You are looking at a river, wide, brown, slow. Somewhere beneath that surface, right now, a crew is driving interlocking steel panels into the riverbed, one by one, each panel slotted into the next like the teeth of a zipper, until they form a wall. A wall with no purpose except to tell the river to stay out. When that wall is finished, pumps will drain the water from inside, and workers will climb down onto a riverbed that minutes ago was 8 meters underwater. They will pour concrete, they will build a bridge pier, and when they are done, the wall comes out, the river closes over the site, and nobody driving across that bridge will ever know that the ground beneath them was borrowed from the water and given back. This is not unusual. This is how it has been done for 2,000 years. The Romans did it with timber, we do it with steel. The principle has not changed. If you want to build something underwater, your first job is to get the water out of the way. But that is only the beginning, because over the last century, engineers have invented methods so improbable that they sound like fiction. They build entire tunnel sections on dry land, seal them like submarines, float them out to sea, and sink them into trenches on the ocean floor. They lower workers in pressurized chambers to the bottom of rivers and ask them to dig. And they send machines the length of a football field boring through solid rock beneath the seabed, building a finished tunnel behind them as they go. Today, we are going to walk through every major technique that makes underwater construction possible, from the simplest to the most extreme. From a ring of steel in a river to a robot on the floor of the deep ocean. By the end, you will never look at a bridge, a tunnel, or a pipeline the same way again. Before we dive in, drop a comment and tell us where you are watching from right now and what time it is there. We want to see how far underwater engineering reaches. If you enjoy long-form engineering breakdowns that go deeper than what you find anywhere else, take 1 second to subscribe. It costs nothing, and it tells us these deep dives are worth making. The cofferdam is the oldest, simplest, and most widely used technique in underwater construction. The idea is pure common sense. If you need to work somewhere that is underwater, build a temporary wall around it, pump the water out, and pretend the water isn't there. The name tells you what it is. Coffer means a chest or a box. Dam means a barrier against water. A cofferdam is a box that keeps the water out. But how do you build a watertight box in the middle of a river? That is the part most people never think about. First, the engineers have to know what is underneath the water. Before a single pile goes in, a cone penetration test device is lowered to the riverbed. A conical steel tip is pushed slowly into the soil, and sensors measure the resistance at every centimeter of depth. What they are looking for is bedrock, the hard layer beneath the mud, sand, and gravel. When the resistance value suddenly jumps, that is the rock. That depth determines how far the sheet piles must be driven. If they don't reach the bedrock, water will seep under the wall and the cofferdam fails. With that depth confirmed, the first step of construction begins. Guide piles are driven into the soil using a hydraulic pile-driving hammer. These are the reference points, the skeleton that tells the sheet piles where to go. Then the sheet piles themselves go in. These are long, corrugated steel panels, each one with an interlocking edge on both sides. The connection is clever. One panel slides into the next like a tongue into a groove, creating a continuous wall of steel that is nearly watertight from the moment it locks together. The machine that drives them down is worth understanding on its own. It does not simply push the piles into the ground. That would be like trying to push a knife into packed sand with your palm. It barely moves. Instead, the driver uses vibration. Inside the machine, 2 eccentric weights rotate in opposite directions. The horizontal forces cancel out, but the vertical forces compound, creating thousands of tiny, fast, powerful pulses per minute that liquefy the soil around the pile and let it slide downward through material that would otherwise resist it. Completely. Watch the pile when the machine is running. You can barely see the vibrations, but the pile sinks into the seabed like a hot knife into butter. The sheet piles are driven from the corners inward to maintain alignment, one by one, interlocking, forming a closed ring of steel around the work area. So the wall is built, the box is closed. Now what? You pump the water out, right? Not so fast, because the moment you start pumping, something tries to kill the entire structure. As the water level inside the cofferdam drops, The pressure from the water on the outside does not. The river is pushing inward with the full weight of 8 meters of water. The inside is empty. If nothing is done, the sheet piles buckle inward, the wall collapses, and the river takes everything back in seconds. So before the water is fully pumped out, a bracing system is installed inside the cofferdam. Horizontal steel beams called struts span from wall to wall, connected to vertical members called wales that run along the sheet piles. The connections are bolted tight. The struts push back against the inward pressure, and the cofferdam holds its shape. But even after all that, engineers still had another problem, a quieter one, and this one they could not brace their way out of. Even with the walls sealed and the bracing holding, water finds a way. It travels under the sheet piles, through the soil, following the pressure difference in a U-shaped path, from the high-pressure river outside, down beneath the wall, and up into the pumped-out interior. This is seepage, and it never stops. So the pumps keep running, day and night. Every cofferdam is a war of attrition against water that is constantly trying to get back in. Once the interior is dry enough to work, the soil above the bedrock is excavated using clamshell buckets. Massive steel jaws operated by a crane, biting into the wet mud and lifting it out scoop by scoop. When the bedrock is reached and cleaned, the real construction begins. But here is a question most people never ask. How do you pour concrete when the floor is still wet? Seepage water is pooling on the bedrock. Normal concrete would be ruined on contact. The answer is a method called tremie. A tremie is a long, watertight steel pipe with a funnel at the top. The pipe is lowered until it touches the bottom. A plug of foam or rubber sits inside the pipe, separating the concrete from the water below. Concrete is poured into the funnel, and the weight of it pushes the plug down and out, displacing the water at the bottom and replacing it with concrete. The critical rule: the lower end of the tremie pipe must stay submerged in the fresh concrete at all times during the pour. If it lifts above the surface, water rushes in, washes the cement paste out of the mix, and the concrete is ruined. So the pipe is raised slowly, centimeter by centimeter, always buried in the concrete it is placing, building a dense, uniform layer from the bottom up. This seal course bonds to the bedrock and to the sheet piles, creating a watertight floor that stops seepage dead. Now the interior is genuinely dry. Workers lay reinforcement bars, build formwork, pour concrete for the bridge pier shaft, and let it cure. A typical bridge pier takes 14 to 28 days to reach full strength. When the pier is strong enough to stand on its own, the cofferdam has done its job. The bracing is removed. The enclosure is flooded. The sheet piles are pulled out of the soil and taken to the next site. The river closes over the spot as if nothing had ever happened. The next time you drive across a bridge over a river, look down at the piers standing in the water. Every one of them was built in the dry, inside a temporary steel box, on a riverbed that was exposed to the air for a few weeks and then given back to the river forever. Cofferdams are brilliant in shallow water, but they are temporary structures and they have a hard limit. Push past about 12 to 15 meters of depth and the bracing becomes impractical. The walls want to buckle. The seepage overwhelms the pumps. So engineers needed something that could go deeper, stay permanently, and become the foundation itself. A caisson is a massive prefabricated box, usually reinforced concrete, that is sunk through the water and into the soil to become part of the finished structure. The cofferdam comes out when the job is done. The caisson stays forever. The simplest version is the open caisson. A hollow concrete cylinder is placed on the riverbed, and the soil inside is excavated by clamshell or suction, scoop by scoop, until the caisson settles through the soft ground and rests on solid bearing material. Then the interior is filled with concrete, and the caisson becomes a permanent foundation pier. But the version that changed engineering history is the pneumatic caisson, and it works like a diving bell turned into a construction site. Picture an enormous concrete box, open at the bottom, with airtight walls and a sealed roof. At the base, there is a working chamber. The box is placed on the riverbed, and compressed air is pumped into that chamber. The air pushes the water down and out through the open bottom, creating a dry workspace deep underwater, with nothing but air pressure holding the river back. Workers enter through airlocks at the top. They descend shafts into the pressurized chamber. They excavate the soil by hand or by machine. As material is removed, the caisson sinks under its own weight. More concrete is added on top to increase the load. The structure slowly settles through the riverbed until it reaches solid rock and stops. The working chamber is filled with concrete, and the caisson becomes the permanent foundation. This technique built the Brooklyn Bridge. In the early 1870s, workers descended into pneumatic caissons sunk to the bottom of the East River in New York, laboring in compressed air chambers more than 20 meters below the water surface. The air kept the river out, but it came at a terrible cost. Workers who surfaced too quickly developed a mysterious illness they called the bends. Nobody understood it at the time. The high air pressure forced nitrogen from the atmosphere into their blood. When they returned to normal pressure too fast, the nitrogen came out of solution and formed bubbles inside their veins, their joints, their spinal cords. The pain was excruciating. Some men were paralyzed. Some died. The chief engineer, Washington Roebling, was himself permanently disabled by the condition. He spent the remaining years of the project watching construction through a telescope from his apartment window across the river. They had invented a way to work at the bottom of a river. They had not yet understood the price the human body would pay for breathing air where air was never meant to be. Today, pneumatic caissons are used with strict decompression protocols, but the technique has been largely replaced for the deepest work by methods that keep human beings entirely out of pressurized environments. Because while some engineers were solving the problem of building foundations beneath the water, a completely different group was solving a far more ambitious question. Not how to build something at the bottom, but how to build something that runs through it. This next technique is the one that most people have never heard of, and it is responsible for some of the most important tunnels in the world. The logic is so counterintuitive that it sounds like a joke. Instead of digging a tunnel through the rock beneath a river or an ocean, you build the tunnel on dry land, in sections. You seal both ends watertight. You float the sections out onto the water. You tow them into position, and you sink them. You are building a tunnel by floating it. The process is mesmerizing in its precision. It begins on shore, in a purpose-built factory or dry dock. Workers construct enormous rectangular concrete boxes, each one a complete section of the finished tunnel. Internal walls divide the box into traffic lanes or railway tubes. Ventilation ducts are already in place. The waterproof membrane is already applied. Every detail of the finished tunnel is built on land, in controlled conditions, before the section ever touches water. The dimensions are staggering. On the Öresund link between Denmark and Sweden, each element was 176 meters long, 40 meters wide, 9 meters high, and weighed 55,000 tons. On the Fehmarnbelt tunnel now under construction between Denmark and Germany, the elements are even larger, 217 meters long, 42 meters wide, and weighing 73,000 tons each. That is roughly the weight of 10 Eiffel Towers in a single concrete block. And yet, because the elements are hollow, they float. The sealed concrete box contains enough trapped air to make it buoyant. Temporary steel bulkheads seal both ends. The segment is towed out of the casting basin, through a gate, and onto the open water, pulled by tugboats to its final position with satellite precision measured in centimeters. Meanwhile, on the seafloor below, a trench has already been dredged to receive the segment. The bottom of the trench is leveled with a gravel bed, laser graded to tolerances of less than 30 millimeters. The margin for error at this scale is smaller than a ruler. When the floating segment arrives overhead, controlled amounts of water are pumped into ballast tanks built into the element. And inch by inch, the 73,000-ton block descends through the water, guided by cables, winches, and surveying systems that would be familiar to a spacecraft docking crew. The positioning tolerance for each element is less than 30 millimeters horizontally and 50 millimeters vertically. 73,000 tons, 30 millimeters. Now here is a question. How do you connect two of these 73,000-ton concrete blocks underwater without sending a single diver down? No underwater welding, no bolts, no sealant gun. The joint is made by water pressure itself, and it is the most elegant trick in all of underwater engineering. Each segment has a massive rubber gasket around its end face. When the new element is lowered into contact with the previous one, temporary steel bulkheads seal the narrow gap between them. The water trapped in that gap is pumped out, and the moment the gap is emptied, the full weight of the ocean pressing on the far end of the new element becomes an unbalanced force. It pushes the new segment tight against the old one with thousands of tons of force, compressing the rubber gasket into a perfect watertight seal. The ocean itself closes the joint. No human hand touches it. The same force that would destroy the tunnel if it leaked is the force that prevents it from leaking. This technique was first used in 1910 beneath the Detroit River. It has worked so reliably that immersed tubes now carry motorways and railways under harbors, rivers, and open seas around the world. The Øresund Tunnel used 20 elements. The Fehmarn Belt, now being assembled in the world's largest tunnel factory on the coast of Denmark, will use 89. The longest immersed tunnel ever built, running 18 kilometers under the Baltic Sea, scheduled to open in 2029. The tunnel is manufactured on land, floated on water, dropped into a ditch. And the ocean, the thing that should make the project impossible, is just the delivery route. If you're appreciating how deep this goes, this is the right moment to hit like. It genuinely helps the algorithm show these long-form engineering deep dives to people who actually want to learn something real. Because the next method handles the jobs too deep for anything we've covered so far. When the water is too deep for a coffer dam, when the soil is too soft for a caisson, when the crossing is too long or too deep for immersed tubes, what do you do then? You go beneath the seabed itself, and you bore through the rock. A tunnel boring machine is a factory that eats mountains. At the front, a rotating cutter head studded with steel disc cutters grinds into the rock face. The head can be 5, 10, even 15 meters in diameter. It turns slowly, under enormous hydraulic pressure, and the disc cutters do not cut the rock the way a drill bit does. They fracture it. Each disc presses against the surface with hundreds of tons of force until the rock gives way in chips and flakes, falling onto a conveyor belt that carries the debris backward through the completed tunnel. But here is the part that makes a tunnel boring machine different from every other excavation method. It does not just dig the hole, it finishes the tunnel behind itself as it moves forward. While the cutter head advances, a system of robotic arms swings precast concrete lining segments into place behind the shield. Each segment is curved to fit the tunnel profile. They are locked together into rings, one ring per advance cycle, and before the rock has time to shift or collapse, the tunnel has a permanent concrete wall. The machine does not stop. The cutters grind forward. The conveyor removes the rock. The arms place the lining. Grout pumps inject liquid cement behind each ring, filling every gap between the concrete and the raw rock, hardening within hours, sealing the tunnel against water and pressure. The tunnel boring machine builds a finished, watertight tunnel from the inside out, leaving a completed structure in its wake like a worm leaving a perfectly lined hole behind it. This is how the Channel Tunnel between England and France was bored. 50 kilometers of tunnel, much of it beneath the open English Channel, cut by 11 tunnel boring machines, working from both sides until they met in the middle with an alignment error of centimeters. It is how the Seikon Tunnel in Japan was driven through volcanic rock 240 meters beneath the Tsugaru Strait. And it is how the Marmaray Tunnel was bored beneath the Bosphorus in Istanbul, connecting Europe and Asia underground for the first time in history. Each of those projects deserves its own video, and if you want us to take one of them apart, say so in the comments. We have already decoded the Seikon Tunnel on this channel, and the story is far stranger than you would expect. Everything we have discussed so far connects two pieces of land beneath a body of water. But what happens when the destination is not the other shore, but the water itself? Some structures are built not to cross the ocean, but to stand in it, permanently, in open water, at depths that would crush anything not designed specifically to survive them. Offshore oil platforms represent the most extreme form of underwater construction ever attempted by human beings. And the foundations they stand on are engineering objects that most people never think about. In shallow water, up to about 150 meters deep, the standard approach is the jacket platform. A tower of welded steel tubes is built on its side in a shipyard, towed to the drilling site, and then upended into a vertical position by controlled flooding of its base. As the heavy end sinks, the tower rotates until it stands upright and is lowered to the seabed. Steel piles are driven through the legs of the jacket, deep into the ocean floor, anchoring the entire structure against waves, currents, and storms. But what about deeper water? How do you anchor something to the ocean floor when the floor is 300 meters down? You don't anchor it. You make it so heavy it holds itself down. Gravity-based structures are enormous concrete platforms, some taller than skyscrapers, built in sheltered Norwegian fjords and then towed out into the open North Sea and sunk onto the seabed under their own weight. The Troll A platform stands on a concrete base that reaches 303 meters from the seafloor to the surface. That is taller than the Eiffel Tower. It was towed into position and lowered. The tallest structure ever moved by humanity, placed on the ocean floor. And in the deepest water of all, 1,000 meters, 2,000 meters, even deeper, the seabed becomes a work site where no human being can survive. Remotely operated vehicles, controlled from ships on the surface through kilometers of cable, descend into total darkness. They install wellheads, they connect pipelines, they tighten bolts and operate valves in water so cold and so pressurized that a human body would not last a second. No cofferdam, no caisson, no pressurized chamber, just robots, cables, cameras, and the patience to work in a place where light itself barely reaches. What connects all of these methods, from the Roman timber cofferdam to the deep-sea robot tightening a bolt in total darkness 2 kilometers beneath the surface, is a single idea that has driven underwater construction for 2,000 years. Water does not want you there. It does not negotiate. It does not get tired. It does not make mistakes. It pushes with the full weight of every molecule above it, against every seal, every joint, every wall you build, every minute of every day, forever. And the only way to build beneath it is to find a system where the water's own physics either works for you, as it does in the immersed tube joint, where the ocean's pressure is the very force that seals the tunnel shut, or can be held back just long enough to finish the job. Every bridge you drive across, every tunnel you ride through, every drop of oil pumped from beneath the sea. It all began with someone looking at water and deciding, I will build there anyway. Every megastructure we take apart on this channel starts with a single question. What should we decode next? That answer is yours. Put it in the comments, and the next deep dive might be the one you asked for. Hit subscribe. Turn on notifications. The next structure goes even deeper. We will see you down there.